Okay, good morning, everybody. So I hope you're having a good day so far. So today we'll continue our discussions about tests for convergence of infinite series. We started off last time with a quick introduction to the a more formal definition of a convergent of a series and its convergence. We say that a series will converge if the sequence of partial sums will converge. But as you have seen, that would be difficult for most for most series. We considered an example with a what do you call this with the telescoping series. And even with the telescoping series, which is basically the intended the target series for for partial sums, it's not that easy to expand everything out and look for a pattern for the partial sum and take the limit of the sequence of partial sums, and if it's finite, then we say it's convergent, right? So it's a lot of work to determine the pattern, and for most complicated series, that might not be practical to do. So what we'll do is to develop some tests to handle those type of more complicated series, but most of them will be hinged on comparing those series with some known ones or some basic ones. I think we talked about them last time, or some of them last time. We started with geometric series, and we said that, okay, if you have a series whose terms in the summation is of the form a constant multiplier, times a ratio raised to the power n, it will converge if and only if the magnitude of the base is less than 1. And not only that, we also know what would be the sum of the series. The sum of the series would be a over 1 minus r. But again, this only works if the magnitude of r is less than 1. Otherwise, it would be divergent. Another helpful type of series would be the p-series. In this case, you have probably a constant all over n to the power p. So the indexing variable is the base, and the exponent is a constant. It will be convergent if p is greater than 1. Otherwise, it will be divergent. The special case of a p-series is when p is equal to 1, and we call that the harmonic series. And the harmonic series automatically, put it in your minds, is divergent. Okay. Now we'll use some of these in the other test. I think we'll use them in limit comparison test a lot, and also in direct comparison test. So I hope you already finished in the lecture the integral test and the limit comparison tests. Is that correct? Yeah, because I guess the target for this week is our section 9.4, 9.5, and 9.6. So that's a lot of material to cover. So did you finish on 9.4 already?
I think we did.
Okay, yeah, great. So yeah, we'll do a quick review of some of the problems here in worksheet 15, then go to worksheet 16. Let me see. I think Daryl sent in a question. I think we did this last time. Let me check. Okay, yeah. But before doing that, let me just finish this recap. We also have this basic info or basic facts about series. A convergent plus another convergent series is convergent. A convergent plus a divergent series is also divergent. Oh, by the way, you could also replace the pluses here by minuses. So convergent minus convergent is also convergent. Convergent minus divergent, or the other way around, is also divergent. A constant, a non-zero constant times a convergent series is convergent. Non-zero constant times divergent series is divergent. And if two series differ only in the first few terms, then they will both converge or both diverge. Now we look at this is the very basic test that I think this is the first thing that you should try. If the series will not fall under the special cases we have just enumerated, do the basic test for divergence, though it would be limited in scope because it will only apply if the limit of the nth term is not equal to 0. So you look at your series, take a look at how an looks like, and then at least mentally you can check what is the limit of an. If the limit of an is not equal to 0, then you're good because the conclusion is that the series diverges. If the limit is 0, there could be no conclusions made out of that case, right? So the BDT, or the basic divergence test, will not apply if the limit of AN is equal to 0. Okay. Now, I guess we did a couple of examples last time. Let me see, Daryl. I think we already did the question you sent. Let me see. Oh, we did something similar to it. We did, yeah, summation of 5 over k squared minus k going from 2 to positive infinity, which is very much similar to what you sent. Okay, maybe I'll do that. Everything, right? And this will be a nice example of how to handle telescoping series, right? So let me see. Though they are very much familiar, let me choose another one, which might be a little more difficult than what you sent, but the process would be the same. Okay, let's try, say, problem 40. Okay. Oh, before going to problem 40 here, which I hope is okay with you, Daryl, the process that you'll use for a specific problem will be similar to what I'll do in problem 40. But before doing that, let me go to Muriel's question. She said, for the written homework, there's a lot of problems that ask the limit of the problems. Can we say that, like, the denominator is growing bigger, so the limit is approaching 0, or do we have to do all of the limit to prove it? Well, for me, as long as you write an explanation saying that, saying what you just said in the chat, that the numerator, that the denominator is growing much faster than the numerator, then I think that is sufficient to say that the limit is equal to 0. So for instance, I assume Morel's this is about Morel, this is about sequences. So say if you're given the sequence 2 to the power n over n to the n, if this is your sequence, then you can say, I'll say that the solution could be something to the tune of saying that the denominator grows faster than the numerator. Because I think you were given in class the hierarchy, in the lecture, the hierarchy of growth of functions, right? So we know that n to the n grows fastest among all of the functions, even beating factorials and exponentials, right? So limit of 2n over n to the n as n goes to infinity is equal to 0. And I guess that's fine. But we will be looking for the reasoning behind it. So please put that into writing and then you're good to go. All right. Okay. Now let's try problem 40. So my hunch is that it would be a telescoping series. Telescoping series are usually disguised as a fraction with a complicated denominator, right? So for such a series, what we do is to look at the partial fraction decomposition. So here we note that 1 over k plus 2 times k plus 4 is equal to a partial fraction decomposition. The denominator is already factored. So the partial fractions will have denominator k plus 2 and k plus 4. So basically the format of the partial fraction decomposition is the same as what we did in chapter 8, though we did that in the context of integrals. The same principle will apply for series. Okay. Now, since the denominators are both linear in terms of the variable k, so we'll put generic constants for the numerator. And then we'll go ahead to solve for a and b. Now we'll use again the same technique we did in chapter 8. So we multiply both sides by the denominator of the original fraction. So this will become 1 equals a times k plus 4 plus b times k plus 2, which is true for any k, right? And we'll take advantage of that fact. So here I can choose k to be the killer value. So I can let k to be equal to minus 4. Because if I do that, we'll have 1 equals negative 2b, right? So that means b is minus 1/2. And if we take k to be equal to negative 2, we'll have 1 equals 2a, implying a is equal to 1/2. So therefore, the original series that we were given and then the summation starts there. Summation starts at 0 to positive infinity is equal to the sum of the partial fractions 1/2 over k plus 2 plus negative 1/2 over k plus 4. K going from 0 to infinity. All right, is that good? So I hope you are following. Now, what I'll do now is to simplify things a bit. I'll factor out the common 1/2 factor. So this would be 1/2 times the summation from 0 to infinity of 1 over k plus 2 minus 1 over k plus 4, which is basically a telescoping series because you will see when I expand the partial sums, the middle terms or most of the middle terms will cancel each other out. Okay, all good so far?
Yes, all good.
Okay. Now, for telescoping series, what we do is to look at the sequence of partial sums and take the limit of the partial sums. So here, we can start with the first partial sum, s sub 0. That would be the beginning k value, right? So s sub k, where k is the starting value, 0. Okay. So if we plug in 0, we get what? We'll get 1/2 minus 1/4, right? That is essentially what I'll get when I plug in k equals 0. Now the second partial sum S1 is the sum of the first two terms. So you'll take the summation from 0 until 1. So if you plug in 0, we knew we'll get, actually I forgot the 1/2 in front, right? Remember there's a 1/2 in front there. And then when k is 0, we get this. Now the second partial sum, I'll plug in, I'll copy the 1/2 multiplier, and it would be 1/2 minus 1/4. That's the value when k is 0. And then when k is 1, what do we get? We get 1/3 minus 1/5. Right? That's the second partial sum, the sum of the first two terms in the series. So I think we cannot do anything yet for this. So let's continue on and try to see the pattern. So far, I don't think we can see a pattern. So I'll continue with expansion. So I'll take what? I'll take S2, which is basically 1/2 times the first two, the sum of the first two terms. Oops. Plus the thing I'll get when I plug in s equals 2. If I plug in k equals 2, I'll get 1/4 minus 1/6. Right? That's the third partial sum. And we see here that, oh, I have a minus 1/4 here. I have another minus 1/4 here. And I think that's it. That's all I get. Now the pattern is not yet obvious, so let's move on and try one more. Let's look at the S3. S3 is 1/2 times whatever we got so far, because we're doing the partial sums, right? So copy this over. Plus, what do we get when we plug in k equals 3? When k is 3, we get 1/5
Minus 1/7.
minus 1/7.
And then those 1/5 will cancel out too.
Exactly. So we'll get minus 1/5 there. We get 1/5 here. And okay, do we see a pattern here? Well, I guess 1/2 will remain. There's no way 1/2 will be canceled because no 1/2 will turn out to be in the last end of the in the latter terms in the partial sums, because what we observe is that it would be increasing, right? The denominators will be increasing, so we will not encounter a 1/2 in the end of the summation, right? So it seems that 1/2 will be a mainstay, as well as 1/3, right? So we are past 1/3, so I guess 1/3 will remain. Will 1/6 remain?
I think it'll do the next sequence, right?
Yeah, because if we look at S4, we will have a plus 1/6 minus 1/8, right? So 1/6
Okay.
will be canceled, but okay. So that means that will be canceled. So only 1/2 and 1/3 will remain. But in the tail end of the partial sums, I guess we'll have the last two negative fractions will remain, right?
Mm.
Yeah. Similarly, here we'll have 1/2 plus 1/3, they remained, and then we only have two negative terms lagging in the partial sum, right? So I guess the pattern, we can now guess the pattern. Oops. So here I think the pattern would be S sub k would be 1/2, the constant multiplier, 1/2 plus 1/3, because we concluded they will not be canceled anymore. But what would be the last two terms? We expect there would be two negative fractions at the tail end, right? Now let's see what do we get here. When we have S2, what remained would be negative 1/5 and negative 1/6. When at S3, what remained are minus 1/6 and minus 1/7. So what I'm guessing here is we'll get what? Minus 1 over, would you agree this would be k plus 3? Because when k is 2, what remained here is minus 1/5. And that fits in there. When k is equal to 3, what remained is minus 1/6. And so I'll get minus 1 over 3 plus 3, right?
Yes.
What do you think would be the last term?
Okay.
K plus, okay, Maria is correct. It's going to be k plus 4. Because here, when k is 2, we get 1/6. When k is 3, we get 1/7. And so this would be 1 over k plus 4. All right. So now we have a general formula for the k partial sum, and it is telescoping because imagine if you have a large summation, but ended up with only 4 terms. That means some of the middle terms or most of the middle terms cancel each other out. So no matter how long the partial sum you consider, you'll end up with only 4 terms. Okay. And this is the general formula for that. So we have the general formula for the partial sums. So all we need to do is to take the limit of the kth partial sum as k approaches infinity. And this would be the limit of 1/2 times the partial sum we have as k approaches infinity, right? But as k approaches infinity, this guy goes to 0. This guy will also go to 0. So we'll be left with 1/2 times 1/2 plus 1/3. And so this is 1/2 times what? 5 over 6. And Marl is right. It's going to be 5 over 12. Okay? So the sequence of partial sums converges to 5 over 12. So that means the series is convergent. And in particular, it converges to 5/12. Okay? All right, so that's how you handle telescoping series. So a lot of work because we need to determine what's the formula for the Kate partial sum. But once you get the Kate partial sum, we expect some of them will cancel each other out.
Hey,
Okay.
Neil.
All right. So okay, Michael sent a question. Okay, which is also a nice review of what we did last time. Okay. Oh, I'm not keeping track of the numbering for the problems anymore, but I'll just label them by bullets. So 5 over 9 to the power k. Now, Michael, this screams geometric series to me because you have something raised to the k, but there is probably a meddling 5 over there. But you can rewrite it. Uh, you can rewrite it as uh, a product of the form a times r to the power n. By the way, Daryl, is it the same question? Yeah, because I didn't answer your question exactly. I used a different one, a slightly different one, but the process should be the same. Okay. Okay, so going back to Michael's question, you can write it as sum of 5 times 1 over 9 to the k. K goes from 0 to infinity, right? Though this doesn't look like a geometric series, but playing a bit with loss of exponents will let us see that this is just 1 over 9 to the power k. So here it's a geometric series with a equals 5 and r is 1 over 9 with the magnitude of r less than 1, right? So remember, geometric series would be of the form like this. So a is 5, r is the base, which is 1/9, and the magnitude of r is 1/9. The absolute value is 1/9, less than 1. So it is convergent with sum equal to, remember, it's a over 1 minus r. That formula will apply whenever the magnitude of r is less than 1. So this is 5 over 1 minus 1/9. So that's 5 over 8/9. So that would be 45 over 8. All right. So for geometric series, you'll just need to play with the given term, with the given terms, and then try to rewrite it in the proper form. Okay. Now let's see. Before leaving worksheet 15, let's look at some examples of the basic divergence test. Let me see. Okay, let's try some of these here. Okay, so look at what can we consider? Okay, so for instance, problem 44 is divergent, right? Because limit of 2 to the k plus 1 as k approaches infinity is equal to positive infinity, obviously not equal to 0. So it's divergent. So this is divergent. What else? Let's try problem 52 below. Yeah, Herson, that's correct. So uh, ideally, to find the limit of the sum, or sorry, to find the sum of a series, you need to look at the sequence of partial sums and then get the limit of that. But there are some sequences, there are some series with known formulas or derived formulas already for the sum, like the geometric series. So if you're given a geometric series and you are asked for a sum, you don't need to go to the sequence of partial sums. So what you'll do is to get, apply the formula. But for other cases, you go back to the definition, get the limit of the sequence of partial sums. Let me see that, Daryl, if that is true here. So I look at the limit of k to the power 1 over k as k going to infinity. The thing here is that this is of the form infinity raised to the 0, which is indeterminate, right? You need to remember L'Hopital's rule, the complications of complications of indeterminate forms. So if you have a very large number, which is our base because k approaches infinity, raised to something that is closer and closer to 0, it won't be equal to 1 necessarily. It's an indeterminate form. And we need to do a little bit more work to evaluate this. So what I'll do here is to consider the real valued counterpart, say limit of x to the 1 over x as x approaches positive infinity, which is an indeterminate form, infinity to the 0. And what I'll try to do is to let y to be equal to x to the 1 over x, which is a review of what you did in Calculus 1. Whenever there's an indeterminate form due to an exponent, we'll take the natural logarithm. So it's helpful to make this substitution, y equals x to the 1 over x. Take the natural log of both sides. Okay. But the nice thing about taking the natural log of both sides is I can use loss of logarithms that will allow me to write the exponent down as a coefficient, thus freeing us up of the problem of the indeterminacy, right? Because the indeterminacy of the given limit was brought about by the exponent that is close to 0. Now we were able to bring that exponent down, so hopefully the limit now would be easier to compute. So we take the limit of both sides as x approaches infinity. Okay. But remember that here we're taking the limit of ln y, but the original problem is to take the limit of y. So there is an extra step to be done after we evaluate this limit, but just keep that in mind. Right, so if we evaluate the right-hand side, we see that, oh, this would be 0 times infinity, still an indeterminate form. But I can rewrite it as ln x over x as x approaches infinity. Now we can view this as an infinity over infinity. L'Hopital's rule will apply. Hopefully you still remember that guy. So it says that you take the derivative of the top over the derivative of the bottom. Derivative of the top is 1 over x. Derivative of the bottom is 1. If we simplify, we'll simply have the limit of 1 over x as x approaches infinity. And this is equal to 0. Okay. But remember, I have a caveat earlier that what we're evaluating here is the limit of ln y, but the original problem asked for the limit of y, right? So therefore, we concluded the limit of k to the power 1 over k, the original problem, which is the same as the limit of x to the 1 over x as x approaches infinity, which we solved using L'Hopital's rule, is equal to e raised to the constant value that we computed. And this is equal to 1. All right. So the limit is equal to 1. And Daryl turned out to be right. The limit is equal to 1. But this is not equal to 0. So the series k to the power 1 over k as k goes to infinity is divergent by the basic test for divergence. All right. And I hope it makes sense why it is divergent. Remember, we say it would be convergent if we'll get a finite sum. It will be divergent if you cannot get a finite number out of the infinite summation. Oops, sorry, wrong notation there. I think we start at 1 until positive infinity, right? Now, what does this say? Tell us? It's telling us that in the long run, what you'll see in the summation would be numbers close to 1. So if you will expand this guy, you'll have number plus number plus number plus some number plus, if you are in the tail end of this, in the tail end of the sum, the terms will become very, very close to 1, right? Because that's what this limit statement is telling us. It's telling us that in the long run, the terms will look like 1. So there would be infinitely many numbers close to 1 at the tail end of your summation. Then it's impossible to get a finite answer out of this. So that's why, that's the theory, or that's the motivation behind the basic test for divergence, or the basic divergence test. If in the long run, the terms in the sum is not going to 0, then it is automatically divergent. Okay? But you need to be careful again. If the limit is 0, no conclusions can be made. Okay? I hope that's clear. And again, as a suggestion, what you do in finding in testing for the convergence of series, first try to see if it's a special series like a p-series, a geometric series, a telescoping series, or a harmonic series. If it's not one of those, then try the basic test for divergence, at least mentally. If the basic test for divergence is inconclusive, then go on with the other tests. And we'll start talking about two of them, the integral test and the comparison tests, later. Now, going back to Daryl's question, so it is divergent because it didn't result in a number other than 1. The thing there is the limit is not equal to 0. Daryl, so for the basic test for divergence, you look at the limit of an. So essentially what you're trying to see, how do the terms in the tail end of the series look like? So this tells us that in the long run, the terms inside the summation will be numbers that are close to 1. So you will see that in the summation, towards the end of it, right, or as you go along in the summation, you will see numbers very, very close to 1 at the end. So you're taking a sum involving an infinite number of numbers close to 1. So there's no possibility that the answer will be finite. Okay? So if the limit is 2, then that's a bigger problem, because in the long run, you will be adding an infinite bunches of numbers close to 2. And there's no possibility you get a finite sum out of it, right? But if the limit is equal to 0, that means in the tail end of the sum, you'll be adding numbers that are very, very small. So it's possible to get a finite sum. Yeah, Herson, I think I get what you're saying. I hope it's, yeah, let's draw a distinction here. The basic test for divergence looks at the limit of the nth term. So it's telling us how does the terms in the tail end of the summation look like. So if the limit of the an's is not equal to 0, then it is divergent. Okay? This is in contrast to the sequence of partial sums, because if you're looking at the limit of the sequence of partial sums, you're looking at how does the sum look like if I will take infinitely many terms, or if I will get sufficiently a sufficiently long summation, right? So if you take the limit of Sn or Sk, so that's the limit of partial sums. If that converges, then the series also converges. But if you're just taking the limit of an, which is your nth term, and it is not equal to 0, then you're right. The series will diverge. Okay? So again, we are drawing a distinction between the limit of an, as n goes to infinity, and this is what the basic test for divergence is telling us, versus the limit of the sequence of partial sums, which is a different thing. So if the limit of an is not 0, then it's divergent automatically. If you took the limit of Sn and you get an answer, then it will converge, right? So the answer here could be equal to 1, and yet your sequence converges. It could be equal to 3, then the series converges because you're taking the limit of partial sums. But here, it's a different thing. If the limit is not equal to 0, then it's divergent because you're looking at how does the terms or how do the terms in the summation look like in the long run. Okay, so these two guys have different arguments. Yes, Harrison. So if you took the limit of the partial sums, whatever the limit is, that is the sum of the series. And you can say that the series will converge to the limit of the partial sums. Okay. All right, so I hope I'm not making it more complicated than it should be. But again, I want to draw the distinction. Limit of AN and limit of SN. All right. Okay, so can we move on to worksheet 16? I already uploaded a blank version of it in my website, so you can take a look at it. It's about the integral and comparison tests for infinite series. Now, what are these two tests? Well, in a nutshell, the integral test. Okay, there are two criteria before you can apply the integral test. First, if you consider the limit of AN, you can start at any index. Let's just say let's start at 1, though you can also start at 0, it doesn't matter. So if you can extend the function, if you can extend AN into a function, you say AN is equal to Fn, right? And F is a real valued function. Then if F is positive and decreasing, then you can apply the integral test. So what you need to do first, look at the extension of AN to a real valued function, say function F. If the function F is positive and decreasing, then you can apply the integral test. So what's the integral test tells us? If the integral of f of x from 0 to positive infinity converges, then, or maybe I should phrase it this way. Oh, okay, let me just finish my sentence here. If the integral converges, then so does the series. If the integral diverges, so does the series. So that means the convergence of our series is the same as the convergence or divergence of the integral, right? But again, before you apply this, make sure that your function is decreasing and is always positive, right? Otherwise, you cannot apply the integral test. Okay, so that's the integral test. Now the comparison test, there are several versions. But here you will be given a series AN for which you need to determine its convergence or divergence. What you need to do is think of a testing series. And for the testing series, you should know whether that testing series will converge or not. Okay, so think of a series with known convergence or divergence. Okay, say Bn. So Bn is our testing series. So I'm not sure what you did first. Did you do direct comparison test or the limit comparison test? You can do the direct comparison test. So if Bn is larger than An and Bn is convergent, then the series An is also convergent. Okay. So what is the reasoning why this is true? Well, you have a series, a testing series that is convergent. And that convergent series is larger than the given series, right? So that means this has a finite answer. And your sequence, the given series is smaller. So that means this should also be finite, right? So if you're given a series, you can think of a larger convergent series, then your given series will also be convergent, right? Because the given is smaller than a convergent series. Now there's an alternative. There's an alternative thing here. If the testing series is smaller than An, and Bn is known to be divergent, so the given series is divergent. And what's the logic behind this? Well, you have a testing series that is divergent, but the given series turns out to be larger than that divergent series. So you can think of a divergent series to be something that doesn't have a finite sum. So you can think of it, oh, this is an infinite value, or this has an infinite value, and yet the summation of An is larger. So it's larger than an infinite value, so therefore it must be infinite as well. So that's why we can conclude that this is divergent. Okay? So I hope hopefully this is making sense. So I want you to get the idea rather than just memorizing the results from a table given in the lecture or in the textbook. So that's the reasoning behind it. Well, alternatively, though those are the only two cases that we have a conclusions for. So if you have a series that is larger than a convergent series, it's convergent. If the series is larger than a divergent series, then it is divergent. All other cases are inconclusive. Now for another version of the comparison test is the limit comparison test, wherein we need to take the limit of An over Bn. And if it is a constant, if it's a constant value, a constant finite value, then the two series will both converge or diverge. Okay. So the idea here is that if you take the limit of An and Bn, and An over Bn, the ratio will go to a constant value. So that means they will just they grow proportionally to each other. So that means they have almost the same rate of growth. So that means if this is finite, then this must also be finite. If this is infinite, this must be also infinite. So they will both converge or diverge. So that's why it's important that you know the behavior of the sum of BNs. Okay. Now let's try some examples. Perhaps this would be better than just talking about abstract terms. So let's try here. Let me try this one. Okay. 1 over n ln. So again, my suggestion is do BDT first. That might work. But here we see that if you take the limit of this guy, what will happen? You'll have 1 over infinity, right? Because this goes to infinity, this goes to infinity, large number times large number, another large number, and this is 1 over a large number. that will go to 0. So the limit of an is equal to 0, basic divergence test would not apply, right? So we'll move to a more complicated test, and for this one, I'll use the integral test because I can define f to be the function 1 over x ln x, okay, which is always positive whenever x is greater than 0, right? Or actually greater than 1. Because remember here, the summation starts at 1. So I want to look at what happens when x is greater than 1, or greater than or equal to 1. Actually here, I should start at 2, because here ln of 1 is going to be 0. So I'll have a 1 over 0. So this is positive whenever x is greater than 1. And then, well, let's look at this. Is it increasing or decreasing? And note f is decreasing. Why is it decreasing? Because when x increases, the denominator also increases. And the bigger the denominator is, the smaller the fraction is, right? So that means when x is larger, the function value is smaller. So it would be decreasing. It is positive. So I can use the integral test. Now for the integral test, we compute the integral from the starting index. The index starts at 2. So I'll do the integral from 2 to positive infinity of f of x, which is 1 over x ln x dx. All right. But note that here, this is an improper integral because of the upper limit is infinite. So let's turn it into a limit. So we'll do the limit of the integral from 2 to b of 1 over x ln x dx as b approaches infinity. All right. And then I'll compute the indefinite integral first so that I don't need to track of the changes in the upper boundary. In the bounds of integral. So here I can let u to be equal to ln x. So du would become 1 over x dx. And luckily I have that. 1 over x dx, that's going to be our du. All over ln x, but ln x is going to be u. Okay. So this is ln of absolute value of u plus c. And then revert to the original variable. This would be ln of the ln of x plus c. All right. So therefore, the integral from 2 to positive infinity of 1 over x ln x dx being equal to the limit of, we already know what the improper integral is. It's going to be ln of the absolute value of ln x evaluated from the lower bound to the upper bound. Then we'll take the limit as b approaches infinity. All right. Then this would be the limit of ln of the absolute value of ln b minus ln of ln 2 as b approaches positive infinity, right? But when b goes to infinity, this guy will go to infinity. Ln of infinity will again go to infinity. This is a constant, so infinity minus a constant, that will still be infinite. All right. So here we see the improper integral, so diverges. So by the integral test, the series diverges. Okay, because again, the improper integral and the series will share the same convergence property. Okay. Right. Let me see. There's a question in the chat from Morel. Okay. Yeah, Merle, I think, yeah, I think there's a type, yeah, there's sort of a mistake here because we know that n factorial grows slower than n to the power n. So probably an oversight. The limit should be equal to 0, right? Because n to the n will grow faster than n factorial in the long run. Okay. All right, so yeah, I think it's a good time to stop here, though I would have wanted to answer a couple more examples. But probably on Friday, I'll work on more examples for the comparison tests and the integral test. All right. But to facilitate our discussion next time, I hope you'll take time to review how to evaluate for integrals, because that is what we'll be doing for the integral test. All right. Then for comparison test, you'll see that it is sort of intuitive. So yeah, let's do that on Friday. Okay, everyone. Any quick question?
Yeah, I have a question.
Oh, sure. Go ahead.
Could you briefly re-explain the question that Mara posted, that picture?
Yeah. So she sent this one, the limit of n factorial over n to the power n plus 2, right? Now, we know that in the hierarchy of growth rates, n to the n will beat n factorial, all right? Because n factorial would be a product of n times n minus 1 times n minus 2 until you reach 3, 2, and 1. That's n factorial, right? But n to the n would be n times n times n such n's, and then you have a plus 2 there, though the plus 2 won't matter for very large n's, right? So basically, if you do a term-by-term comparison here, you'll see that the denominator always wins.
Mm-hmm.
So that means the denominator will grow at a much faster rate than how the numerator will increase, thereby making the sequence converge to 0.
Oh, okay. Okay. Thank you.
Right. Yeah, there could have been a mix-up there, an oversight. So yeah, I think the limit there should be equal to 0.
Oh, thank you.
All right. So that's it for today, guys. Let's see each other again on Friday. And yeah, I hope you enjoyed the rest of the day. Bye, everybody.